Okay, our next speaker is Christoph Brune from Twente, and Christoph will speak about cancer ID from spectral segmentation to deep learning.
So, thank you very much for the nice introduction and also for the opportunity to talk here. I actually enjoyed very much the discussion we had, so I hope I can continue this discussion at the end of my talk. And you will see a lot of similarities, but now I will show it slightly more from a practical point of view. So I will focus very much on a specific project that we have in the EU, and it is so important that because it really addresses a generic way of analyzing a big health problem, which is cancer, and it is addressing it in such a general way that we hope to get liquid biopsy. That means analyzing blood via cell analysis of patients in such a way that in the future hazard ratios and much more guided therapy is really in reach and clear. So this project is quite large. It has more than 30 participants, including big institutes, university hospitals, research hospitals, but also a lot of companies, including big companies like Bayer or Siemens. So what I want to convince you today is that with mathematics and mathematical imaging, we can already address in some way the most important machine learning questions that they have. We can already bring it to a certain level. That was the first 2 years of this project. And in the second part, I will also show you that this field is really demanding and asking for deep learning. So they need that. And I will show you first results where it is really clear where the difficulties are, and that this discussion we have here right now is really crucial. So it is about from spectral segmentation to deep learning, and this is mainly work I will show today by Leonie Zoyne, our PhD student, that we share with a group on medical cell biophysics and also with mathematics. Actually, Stefan van Gils is our chair on theoretical neuroscience, so here neuroscience, mathematical theory and also ODE theory we just talked about come together. So it's a perfect place where machine learning, data science and mathematics have to interact. So to get an overview and a first motivation why we work on this project with mathematical techniques is that there is a strong mathematical segmentation and classification tasks in such liquid biopsy problems. So the main aim of this Cancer IDEO consortium is to validate blood-based biomarkers, so basically looking at fluorescent images, and a lot of them. And they are usually in advance enriched a little bit so that we see more cells. Why is that so important? These liquid biopsies are taken with a small cartridge. There's blood in there, and they are maybe enriched, but it is like really finding a needle in a haystack. So you see a lot of frames. I will show you some on the next slide. They look like this, and then there are very, very small single elements in hundreds of images, maybe 2 or 3 cells that are tumor cells. And they can look very different in shape and very different in structure. So this will be the main complicated part in my talk. So it has a generative structure, these tumor cells, but what are they built upon? What eigenfunctions do they encounter in terms of mathematical ingredients? So we develop, instead of manual reviewing what they do for years, we now develop in computer-assisted machine learning-based techniques. And in the easiest case, that's actually a commercial system that they have already. That's called Cell Search, a big company developing this for liquid biopsy for years. But they use a very, very simplified segmentation techniques. So what I want to convince you is how we can make this more robust with spectral segmentation. So allowing to overcome this problem of regularization parameter estimation, overcoming uncertainty in the data, and in which way we have to extend that to deep learning. There's a very nice byproduct in this project that is related to parameter estimation and generative data. In literature and biomedicine, there's no definition of a tumor cell yet. So people have an idea that some channels should be active and some color channels should not be active, and that they have roughly a certain morphology, but the rest is quite unclear. So we already found classes of cells with our reconstructions that they have not known before from the commercial system. So that indicates that we most likely will come up with a new definition of tumor cells for textbooks in a couple of years from now. Why is this so challenging? It's challenging because we have different hospitals, different machines, different, so therefore different instabilities and robustness problems. The cells can be quite clustered. They have different filtering systems. So here you see holes in which small cells have to get stopped by so that they can better be measured. But they can also have very different contributions from different color parts. So roughly what you see here is one channel is the skeleton of the cell, like a white blood cell would have as well. The other color is the DNA, so where the core information of the cell is encoded, and maybe other channels tell you something about vesicles on the cell, so something additionally. So why is this so interesting from a sparsity, compressed sensing, graph clustering point of view? These cells are so rich in their different structures in the blood that we already for tumor cell analysis we could think about subclasses that vary in scales in a lot of different ways. So they are cell artifacts, intact cells. So here you see a typical, let's say, perfect tumor cell, but also cells that are nearly destroyed, so apoptotic cells, or vesicles that are even smaller size. And they appear in different numbers. So the question is, can we develop a multispectral approach that gives us this whole distribution at once and shows us also how often they appear and where they appear, and maybe even automatically color code them. So this would be a good starting point, because then we could extract them as maybe thumbnails and do maybe deep learning on them, understanding what is this class of cell mainly based upon versus the ones that are in textbooks up to now. And what was really intriguing for me is that these cells are usually ellipsoid, so they're close to circles, or at least the key ingredients. So these are the simplest eigenfunctions you can think of for maybe Sobolev spaces or functions of bounded variation. So is there a generalization we can find in that sense on the long term? So very simple. Let's start with the arbitrary data sets. You all know spectral transformations, a related filtering. So for example, Fourier wavelets, shearlets. You can think of a lot of transformations, but the main idea is key here. You have a composition of sub-elements that describe your signal, and with the right basis description you can generate data, and the key question is, can you sparsely represent them in those basis structures to make use of. So here it's Hertz, but maybe we find a more general measure that captures these characteristics of the cells. So in other words, is it possible, instead of just signal representation in a sparse fashion, also encode morphology and maybe more general features? So let's step back and look at, first of all, standard nonlinear diffusion. This is a story where regularization parameters, so for a simple filtering variational method, maybe one homogeneous convex functional like total variation, would perform a certain gradient flow in a forward sense. So that means you increase alpha step by step, or in the gradient flow you start with your noisy signal and over time you get more and more diffusive version. In this gradient flow you see that this has not an impact on the structure of the eigenfunctions, like here the one-dimensional TV block, but it has influence on the scale. So here scale means intensity changes. The same thing you can study in an inverse sense, so you can take the same equation but use the inverse scale space method. So it will also have a corresponding gradient flow, but then you would see that the scale is behaving in the opposite direction. So this is very well known. This is inverse scale space methods for arbitrary classes, or not arbitrary, but certain classes that we all use quite well. So data fidelities, regularization functionals, and their corresponding Bregman divergence. So I think most of you know this, but just shortly repeat. The Bregman divergence is nothing else than taking a corresponding convex functional, and for a certain reference point UL, that's the one that you have here, you look at the functional value, and in comparison to the other position U that your distance is based on, you look at a local linearization at that reference point UL. So here that's this tangent, that's the subgradient that you have here PL, and then the Bregman distance is telling you, with respect to that reference point and the tangent, what is the difference between the local linearization, so the first order Taylor expansion, and that reference point of the functional at the other side. So if you take that as a regularization functional and take the corresponding well-defined accumulation of subgradients, you can see that this method is giving you this inverse flow. So it will add back contrast for just denoising. But what does it do for segmentation? That was the question that we wanted to phrase here. Moreover, there's this very nice idea of unfolding for very nonlinear gradient flows, like you can see here, in the same way for as you can do it for Fourier transforms or wavelet transforms. So to decompose for a given data set the whole spectral structure and to have a Parseval identity available, so that the norm is really represented. And that idea came out of those works. And now the question is, can we extend this here not only for denoising, but also for more morphology-based approaches? And what does it mean? So the idea here is that you study this gradient flow by changing the alpha value, and that with respect to the eigenvalue problem, it would show up as one single spike in the second derivative of the gradient flow here. So in the best case, you would observe several eigenfunctions that are significant, and that would tell you quite clearly while you diffuse with the filter when something important comes up. The same thing you can do for the inverse approach. So instead of taking the forward gradient flow, you can take the backward gradient flow. So here we take the Bregman distance that comes up like this. And also for this nonlinear eigenvalue problem, you will see that at some point at a sparse location in time, this eigenfunction will show up as one single step. So when we saw this and had these eigenfunctions in mind, then we wondered, isn't it possible to also use that for segmentation, such that for a full picture of cells, it is possible to first see the small ones, then the next larger ones, and so on. And how does then relate shape with intensity of those cells? Because both is very important to characterize them. So this is the full picture that you need. So not only following this gradient flow, but you also should capture the so-called spectral response. So you have to capture for changing diffusivity, for changing the alpha values, or for changing time in the gradient flow, what is the representation of your signal with respect to their coefficient contributions. So very typical for wavelets and shearlets. But here it has a specific element because you are very free in what kind of functional you use and what regularization term you use. But you see the typical behavior. If you would threshold the spectral response with certain contributions, then you are able to create high pass, low pass filters and to decompose your signal in the key ingredients. So here the hope is this is your cell, and in the ideal case you automatically get what are the vesicles, what are the bigger contributions, and maybe do it for multiple channels simultaneously. I think what is really important that also this is available, and you get a direct representation with respect to your coefficients. So how can we extend this to segmentation and clustering as a basis for more general data analysis? So this model is very well known. This is the active contour model called Chan-Bese model, and it also is based on the perimeter here with the corresponding contour. What is very nice is that it is not only related to the Hamilton-Jacobi equations, but it also allows you to see it in relationship to image denoising with total variation. Because here the TV term is indirectly available, and this term might also be related to denoising when you have binary data. And usually this data that we look at are of binary type. So this slide is just showing you the total variation definition and the corresponding function space. This is showing the relationship of the contour that you have and the related functions with respect to TV. So you can directly take an indicator function and see the relationship. And what is really important here, that's the key, why we could extend this idea from denoising and spectral responses to segmentation, is that if you have a binary constraint in your data, that's what you see here, so binary segmentation, foreground, background, then this segmentation problem is equivalent to studying the denoising problem with the total variation, with this reference function. So you might wonder, yeah, but you have a lot of assumptions here, C1 and C2, and you assume binary approaches. How could you ever find different intensity levels and different shapes? This is something of the surprises that we got from this model. We were just crazy enough to try it and do it. But you will see that although we make this strong assumption here, the actual method really unfolds multiple levels, although the assumption here is 0, 1. And that is because we have a gradient flow that step by step sees 0, 1 differences. For sure, this problem is non-convex, so you have to think about convex relaxations. So instead of actually looking at 0, 1 set, we take the interval 0, 1. And it actually was enough to just update it in this simple way. So taking the constants from step to step via the previous estimate of your reference function. So this is a well-known analytical result. And we use this here as the justification for the inner part of the algorithm. So to summarize this first part, what we used is in the forward scale space sense, just TV denoising and nonlinear segmentation as the counterpart, and the corresponding inverse scale space methods. So is it possible to get something similar for the inverse scale space as well, and how much do they add? That was our question. So now something interesting comes up with respect to parameter estimation. We all know that there's a problem with estimating the regularization parameters for inverse problems. And wouldn't it be nice if you have this unfolding of the scales of the spectral response, and it would automatically give you a regularization parameter choice in that way, without doing full sampling. That's actually what happens here. So if you take this data fidelity for segmentation and take the Bregman distance, and have a fixed alpha, look at the iterates with respect to the subgradient here, then you see that the alpha is updated step by step with a ratio to k, with the current iterate. So in some way it behaves like multiplying in each iteration step the regularization parameter. And that's what you see in the full method. So if you study the segmentation and go through the inverse scale space, then you can transition this P inside. And because you have a very simple local multiplication in your subgradients, this means that you can actually move it outside again. So although you change your regularization functional, it shows up as a change of the regularization parameter. So what does it do for the histogram or for your signal? The Bregman distance is adding contrast back. So that means also for segmentation, it will change the histogram to be better and better separable. So it will really push away the intensities from low values and high values. And for the regularization parameter, it means that you automatically get, instead of a linearly spaced alpha, you get an exponential decay, which is something that as people have found already in the past that this is a possible method. But here it comes out automatically. And keep in mind that this choice here of alpha is really not a sensitive parameter, so we check this. So also for this segmentation-based spectral decomposition, there's a spectral response available. So here we define it like, in the forward case, we study the negative values with changes over time, where t here is the Bregman iteration time, whereas in the it's the opposite. So here the forward case and here the inverse case. But the spectral response can then be, for example, studied with the L1 norm. Maybe L0 norm is also an additional interesting question. So studying the histogram of responses. So let's see how it works and what we can do with it. It's a very simple test example where we see objects that are related to the eigenfunctions of that corresponding functional, in this case TV. We see objects of different scale in the sense of perimeter, but they have the same intensity. So it's already a thresholded object on the left, but let's take that as our input data. We try to automatically identify with this approach, so with a sequence of Bregman iterations, that we have these objects, where the contours are, and maybe how large they are. That would be desired. So what you see is that when you take this Bragg iteration and look at the spectral response, the object, because we have an inverse scale space approach, this very large object comes up, automatically its contour. And because we know that it appears quite early in this iteration, it means that it is the largest object that we can see in this signal. And then the same thing for the second, third, and fourth. So you might wonder, this is a very simple object, you could also just threshold it and maybe do something else. Why is it so useful for our data? It also gives us a color coding that immediately says how different the cells are in certain properties. And it is much more robust, we will also see that, because overall this strategy is well posed. So here's the algorithm. So we used, we have already newer variants of it, but basically a primal dual hybrid gradient method. We parallelized this, and you see that the steps are not more complicated than just for denoising. But it gives you the morphology in a spectral description. That's very nice. Here you see how we compared it with the GPU with the cluster implementation versus a standard dual core implementation. And it basically behaves nicely with respect to the data sizes that we actually need. So we could improve this already, but we are now at a range of, well, for one blood sample, 30 minutes, which is acceptable for now, what we have with these clinical setups. But you see there are a lot of data sets, and it was really challenging to find an algorithm that is powerful and really shows the shape and gives a good indication of robustness, but simultaneously fast enough and really parallelizable. So now you might think that the total variation is not only based on the level set length, but it might also indicate where the jumps appear and how often they appear. So it is an information also about discontinuities and their height. So this is what we tested here. We took the same level set length, but we changed intensity and also applied this inverse procedure. So in the best case, it will also show us an unfolding in the spectral response, and that's what's happening. So we first see the highest intensity object, so the highest total variation, like before, the large object. Then the second one, third one, and fourth one. So again, also this works. And you also see that with slightly nonlinear scaling, you see that the colors indicate what were the highest objects in terms of intensity per channel. This was really the promising part where I said we should continue working on this. This slide shows that how robust this method is, and that it is completely independent of parameter choices. Usually you have to correlate for different noise levels the corresponding regularization parameter, and also there the choice is quite sensitive. But this here came completely for free, and you can also see that when you cut down the spectral response with respect to the elements, then you even get access to the subclasses of objects with this property. But you also see that you have to think a little bit about at the boundaries, for example here, what norms you take, and the question is TV already too restrictive for this case? And yes, it is. And I will show you in which way it was too restrictive. But you see nicely for piecewise constant objects, it works. But what is even more surprising is that our assumption in the model was 0 and 1. But here we have a multi-phase segmentation. So we have different intensities, and they all come up because we take the spectral response. So here is a very simple example where there were not too much crowded cells in there, and you see that the spectral responses are already much more complicated, but it nicely shows you the important classes and their setups. On the screen you see a bit more. And you see that also after a certain point you have basically background noise, so it will be quite easy to look at this response function and separate the subclasses as desired. So with this approach, we implemented this in a software. We had already a lot of success in this field of medical imaging. So here you see some parts of a poster that we presented 2 weeks ago at a very large conference, a so-called circulating tumor cell conference. And we got within one day, we got more than 100 individual users that went to the website and used the software. So just to give you an impression how well it is accepted by the community. So here you see a comparison with expert panels where the experts have a very good understanding of the biophysics in the background, and you see quickly that our segmentation figured out that the very good simple cells were easily detectable, whereas in the cases where the experts are a bit more knowledgeable about some characteristics, it was the reviewers on average, so that used our software, were still a little bit misleading. But what we found out, and that is really the key part with giving this software to them and using it, so that's what the EU IMI key opinion leaders said as well as a review. They said the notable highlight of this overall project is the development of an open source image analysis program, except for automated comparison of circulating tumor cells. As proof of principle, the consortium has demonstrated that this tool has improved, and that's not the important part, it has improved the concordance between operators in assigning CTCs. So this manual task that you had before was really the sensitivity, because there were different machines, different hospitals, and they were all creating their own opinion about what a tumor cell is and how to count them. And this is really crucial, because they have blood samples with 5 cells in there, or 4 cells, and one group would say these are just 4 in there, and the other would say 3. So and we could clearly show that for a very relevant disease marker for breast cancer, so metastatic breast cancers, that with this tool, when they all use the tool, they are much more let's say, develop a joint opinion. So this was a starting point for us. There is maybe a general machine learning based generative design of tumor cells that can be described mathematically. Because they can, just by using the manual classification, the manual segmentation, they can build a better opinion. So let's get back to the functionals I was showing. Instead of the total variation with an isotropic setup, we have choices. So we can change the wolf shapes within the TV definition. So what we're intrigued by is we take the wrong shapes with respect to the underlying model. Is it still able to give a good spectral response, and what does it depend on? So how does the assumption in our models, the shape assumptions, how do they sensitively influence the detectability? That was our question here. So here you see 3 examples that are quite well known to you. So here we would see in the dual space that the edges are really edges. Here we would prefer more the circular shape of cells, whereas here we have more diamond-like structure. And we just took those eigenfunctions and saw when we take the right model, this approach happens to work in the same way. So we see slightly different locations, but it gives sparse responses. What is then interesting is if you take several of those objects, so you have cells that are deformed, have different structures, and you take the wrong assumption, does it still make sense? So here we took obviously the L2 shape, so the isotropic total variation, and you see nicely that over time, so over propagation time, this triangle tries to be approximated via the local TV shape in this inverse scale space. So it propagates till the corner. And it also shows that, so this first peak here relates to, if I remember correctly, these objects. Yeah, I can't exactly remember anymore, but basically what you see is that there are areas where 2 objects can come up, and that means here that these have same size, these have same size, but these sizes are different. So they're similar, but slightly different. But what you see is that the eigenfunctions are reshaped over time, and that is something that is encoded also in these deep learning networks. So we deform the main geometry in such a way that they fit a general representation. So in other words, it works to some extent, but for more general shapes and compositions of shapes, we have to do much more than just simplifying among total variation. So then we had the other problem that total variation does only detect control length and height of jumps. But it also has a contrast loss when you change the intensity levels. So it gives you a separation of scales with respect to intensity. It would be nice to also have access just to the geometry, just the morphology of the objects, independent of what contrast they have. Why is it so important? A lot of data sets that we observe in cell biology or in medical imaging have illumination problems. They have different intensities in vessels, for example. and you still want to segment them. So can we find an invariant measure that gives us the same spectral response, but does not take into account just the intensity changes within objects? And here, the L1 norm is very well known due to these works, where we have a contrast invariant variational method. So we could apply the same procedure. Now the PDE model is much more complicated. So here it's a doubly nonlinear evolution equation with this starting intensity. But what you see if you compare the 2 norm in your inner model with the 1 norm in your inner model, that for this input image, it is nicely detecting just the size of the object, so the perimeter, and it does not step-by-step increase the residual. So this gives you a chance to get into, or hope that the spectral response is even sparser than in the cases I showed you already. And you will see in examples why this is for real situations really useful. How much time do we have?
We have till 10 to...
Yeah, I will not make it too long. We have lunch, right? Okay, so what you see here is a convincing example where you have the binary image that you would like to segment, and we studied what does this method, although we assume a local eigenfunction that is that is a circle, what does it show for more general structures? And you see that the color coding of sizes suddenly give you the diameter of the objects, and it changes its color in the spectral response at the junction points, which was very surprising to us. This happens. And moreover, when you go from the 2 norm in your inner model to the 1 norm, you suddenly, because it is contrast invariant, it clearly gives you a sparser response. But even more, when you look at this already quite good spectral decomposition or spectral segmentation, so here you see the different colors for diameters. If you compare this result to this one, it is nearly the same. Also the spectral response is here. Although you changed the contrast of the input data sets quite a bit. And this will hold also for more and more noise. So what you see is that the robustness is really paying off when you take more nonlinear inner models. But the price is that the computational efficiency here is more difficult. But in this primal dual framework we used, it was similar. And we actually extended this also to a much more complicated case where Yuri and Carola and the hospital here in Cambridge here was involved. So we have retina images with transport, and here the question was, can we extract these blood vessels and the diameter within a very efficient method? And you see that we could show before treatment and after treatment that the retina diameter changes in a histogram fashion quite clearly, and this was also computed in such a way that you see the diameter as color coding. So you really see that you get efficiently different results. So as a summary for this first part, before I show you the deep learning results, is we have a new approach for multi-scale segmentation. The L1 data fidelity really helps to separate intensity from size and morphology. And this toolbox was really a starting point for us to think about deep learning, because that was really asked for from the medical field, and it has such an important implication. The transfer of this overall situation to convolutional autoencoders. So autoencoders are nothing else than denoising networks, so they have input space and output space on the same size. This could be very, very interesting, especially if you think about spectral graph clustering. And for sure, studying the spectral responses for more general operators, more general regularization functions, we see that in the talk from Martin Benning. This is also very interesting from an inverse problems point of view. So this is one of the main messages that Elliot gave at the beginning. I for sure also followed these citations quite a bit previous year. So you see that deep learning has a big influence on the field, and that there were breakthrough technologies like reinforcement learning this year. But it also still remains a mysterious machine, as we have already heard. And I think these citations from you see that all over the place are quite clear. No one really knows how the most advanced algorithms do what they do. That could be a problem. And artificial intelligence is a black box that thinks in ways we don't understand. That's thrilling, but that's also very scary. And I fully agree with that. Thinking about these methods more and more tells us we need to incorporate function representation in the sense of compressed sensing. We also have to incorporate understanding of stability, like ODE, what was shown. But I think also this correlationship to spectral responses or spectral analysis on graphs and how that relates to clustering in deep learning networks, that's very crucial as well. So I think what we have to really work on, and I think that's a perfect place in this conference to do, I tried to do it myself the previous months a lot, is to think about this bridge between math and computer science in this flavor. And I think really in all parts you see similarities between the fields, but with different notations and with different viewpoints. So I think here a structured approach would be very, very helpful, and I'm very interested in helping with this. So here you see a result that we actually used, where we used a nearly shallow network, so a network that Eldad described with formulas. I think already in this case it is quite difficult to write down the inclusion. I think it is possible, but you see they're coming in layers that are of convolution type, so where the K is more of a convolution kernel diagonal matrix. Then you have batch normalization, the hack we talked about. You have activation functions, so here ReLU layer, rectifier linear unit, and max pooling that changes the scale. And then you do that 3 times so that you overcome 1, 2, 3 scales, and then you have a classifying element where the soft max tells you a certain likelihood for a certain class. But it is a fairly simple network, and already in that network you see the problems we heard from Eldad very clearly. And I wanted to share this with you because that motivates really how the first part of my talk relates to the questions we all, I think, would like to address. When you try to look at the intact CTC cells, so the cells that have very nice shape and very close to eigenfunctions, nicely representable by convolutional layers and then their activation functions. So simple objects. The manual approach that I showed works, but it also allows you to learn a network that separates these cells from the rest. But the medical people are really interested in is not understanding what they already know, that these cells are good candidates, but what they really want to know is, can we separate circulating tumor cells from all the other 4 or 5 classes that we have there, and maybe even the new classes that we found now that are also in the blood. Well, that's what I get then. So we took the same network, and instead of 2 classifiers, so having a fairly simple separation after the mapping of the ODE, we took 5 classes, so a very typical case to what Eldad showed you at the end. And we have extracellular vesicles, so those cells. We have white blood cells that are more of a different type than tumor cells, those ones. And we have a new class, which I can't describe really, but that's a novelty that we found via our manual tool. And the rest class that does not fit in any of those. So if you take those ground truth data sets, roughly 10,000 cells, and try to use the same network, you will see that suddenly the accuracy drops, although you were able to separate one class from the rest. So what this tells me is that either this network is not rich enough in scale and representability from layer to layer, or it tells me that this network is not stable enough because I have some more local elements in there that makes this deformation behave like what Eldad shows. But nevertheless, the conclusion here, I think, is really we have several approaches. So here I summarize my current view on it. There are network architectures that we can choose, but we have to make it systematic and clear. So which activation functions to use? So here we can learn, I think, from neuroscience very much. So the people in theoretical neuroscience doing ODE bifurcation analysis, they know exactly from biochemical models of cells, so microanalysis of the brain, they know quite well which activation functions have certain effect. So a typical example is that instead of the rectifying linear unit, so where you say with more inputs to the cells, the cells get more and more active, another option is that you take a Gaussian. So people tend to use more like this. Here, the people in neuroscience would say this makes much more sense for cells because cells get more and more active, and then in practice we know that at some point there is a deadlock appearing because all the cells get so much activity that they are swinging all together in the same time. So this would give an overshoot, and that means that the network is no longer able to work anymore. So it is overfilled with energy. I think these effects we have to understand from numerical analysis in the same way as you've seen in the previous talk, and we have to read what activation layers are really the ones that produce such behaviors. So this is more the inverse view on learning the activation functions, then depth and convolution types. I think this is something that Lars will talk about in the next talk as well. But here really the stability with respect to how many layers and how should they relate to each other is important. The generalized view as an ODE I think is really key. So I fully agree with that. But what we should not forget is really the statistical properties of the patterns. So I think we need a clear bridge of this part to the first part of my talk. So we need something that captures the ODE stability in combination with representability. So what maybe people do in harmonic analysis as well. And the third part is for sure the learning part with respect to non-convex optimization. So here the key question in my opinion is, what is the optimal selection and amount of training data? This has for sure something to do with those. And what we very often observe is that different local minima share the same similar performance. So when we have a more structured and more stable way to do that, I think this will also automatically getting obsolete. But these are the three key questions in my opinion to work on. So as a summary overall, I showed you that deep learning for cancer ID is in principle possible, but there are a lot of open questions which I don't want to give to the applied people, and I need your help to do that more in a more clever way. Because if I give them a method that is robust maybe on all the data sets that they have, maybe in the future they have another data set and they will just try, they will just do it, and they will make implications and write papers within months on this immediately. So I think really in medical imaging there's an ethical need that we do something that this is not going out of order. Eigenfunctions and invariance is really key here, and I think the relationship to neural fields and kernel methods is possible. Maybe one short comment. So we have a new paper on PNAS where it shows that multiscale dynamics happen at a micro scale on the brain. So we make measurements with an Utah array directly on the brain surface and try to imitate what a very, very simple shallow deep learning network with two connective models does. And we saw a similarity of the deep learning network with the one that we have in the measurements, and they show different dynamics. So in my opinion, there is a chance that we can learn from neuroscience and theoretical neuroscience which architectures are working and for which reason. And for sure, scale and stability is something that is crucial also as you think about multispectral representations. So thank you very much for your attention.
Thank you very much.
I'd like to ask some question about the spectral for the skill separation. So what it seems from your test, everything works very well. We have been testing this one on some seismic data. And then clearly we can see the scale, but the spectral doesn't do it. And we plot the intensity, we found out, you see in your test, most of the images are blocky. It gives a constant plus high noise. And then the spectral seems to work. But the data we have, when we plotted the intensity, in fact, is a very smooth function with a reasonable oscillation, but you can see clearly here is bright here, and then the spectral seems it doesn't work. So do you experience something similar with the real data, or mostly it was very, very good?
Yeah, very good question. So exactly that problem we observed, and the reason to overcome that was to transition to the L1 version of it, because there it's still taking into account the contours of your objects, but the local variances, if they are more of TGV type, so maybe locally smooth but not so important, it was still working very, very much. So my short answer would be the L1 version will most likely do it. So taking L1 plus TV and then do a spectral response. But if you want to do it more accurate and more reasonable, I think, and really the shape within the objects matter for seismic. So for example, when you have one layer I don't know, some reservoir of salt, and then you have some, let's say, different subregions in it, and you want to resolve them as well, but still want to see the same contour of the salt, then I think you need another forward model, or more general regularization functional insight. So you need maybe TGV or mixtures of first order derivatives, I think. But I think if we know how to use the deep learning networks, then there will be a counterpart that we can use there as well.
Thank you.
I just have one question, which is, I guess you don't see this so often in biomedical images, but if you have texture that you might want to also your spectral response to flag up, that might be quite difficult to separate this from from actually the noise that you see at the very end of your spectrum. I don't know if the inner structure of tissue could be interesting in certain applications.
Right, it's for sure related to your question, but I think if you really have a very systematic structure, like you would know from non-local regularization methods, then I think the inner functionals really have to be extended to graph-based approaches. So then we would get maybe a spectral decomposition of a graph filtering procedure, and then we are very close to Chiga cuts and what Xavier Brasson is working on and colleagues.
Okay, so
and I think it
shift to the non-local.
I think so. Yeah, that's the only reasonable way, I think, because your prior assumption is so much off that that it makes no sense. So it's really a question of what do you need? Do you need clusters, or do you need to identify the patterns? But I think the spectral representation is still so flexible that you can do at least if it is one homogeneous in some way. You can address that. But that's for sure the key problem here. Learning the graph simultaneously or in advance will be then your sensitive component. That's also clear.
Okay, so if there are no more questions, let's thank Christoph again.